Alright, so welcome to our review session. We have a ton of integrals on this sheet I gave you, and you don't have to do them all. We're not going to do them all. We just want to talk about the styles of integrals that we have. Some of these aren't even on the AP test, but it's a good review of integration in general. So what we have are rewriting integrals, and then we have solving indefinite integrals. We also have, of course, definite integrals, but I'm not putting it on here because if you can find an antiderivative, I'm sure you can plug in your b and your a and subtract. So we're not doing the A and B thing. Besides, we did fundamental theorem last week, so we don't need to redo it. Okay, so the first thing you guys want to do is just rewrite this integral I gave you right here. Try to write it so that it has no x's anywhere. And I mean, you have to also get rid of the dx, you know. So go ahead and try that. No? Okay, so on this one, it is a u sub problem because there's an x squared and there's an x. So you should be able to get away with just letting u equal x squared like we said, and then du is basically 2x dx, and you can put a 1/2 on the left. So this is how I always taught it, and you're going to basically end up then with 1/2 du right here, and then there's a sine u. So basically you end up with this situation. Integral x equals 1 to x equals 5, and then we have 1/2 sine u du. Okay, and then you can update your x and your x equals 1 and your x equals 5. Since x is 1, u, which is x squared, would be 1 squared, which is 1. And when x is 5, u, which is x squared, would be 5 squared, which is 25. So what I'm saying is your new limits of integration are 1 and 25. And those are u values. So you have u equals 1, u equals 25, and you have a sine u, a du, and a 1/2 out front. Okay, so that's just rewriting an integral. Then under solving definite integrals, I have several topics there. We have basic ones, memorized ones. When I say basic, I just mean like algebraic problems. So you guys know if you're integrating x to the n, you're just going to add a power and then divide by your new power. So that's what I mean by basic. I just mean algebraic. Memorized stuff, like if somebody asks you, hey, go ahead and integrate secant, you'll say, oh man, I have to use like a u sub, but you don't. The answer is secant. The answer is secant. Why? Because who's the function where the derivative is secant? It's secant. Secant has this property. The derivative of secant is secant. So sometimes we just go with memorized antiderivatives. See? U substitution is a very, very, very powerful method. We use it all the time. Change of variables, I will mention that today. I don't think any of you know that yet. IBP, tabular free lunge, and partial fractions, those are BC only topics, but you guys have been practicing those this year. So, okay, let's go to, what I want to do now is go down to the bottom, and I want to circle any integral you think can be solved using basic algebraic technique. So that means if you think method 1 is the appropriate method, so let's number these methods. Let's number these methods 1, 2, 3, 4, 5, 6. If we can identify what kind of problems they are before doing them, it will help us plan our attack on the problem. Okay? So just go through and write a 1, 2, 3, 4, 5, or 6 next to each problem. Just use your gut feel, and we'll run through them and see if you're right. Okay, so the first one is actually 1. It's algebraic because if you FOIL it out, you're going to get like t to the 2/3, and there's also going to be 1 over t squared, and there's also going to be like a middle term. But it's all going to be like something to the power, t to the power, t to the power, t to the power. You're going to add a power, add a power, add a power, divide by the 3 new powers. It's definitely algebraic in its appearance. Okay, let's go now to our next one, number 2. Number 2, a bit of a tough call. 3, okay. This is actually a u sub problem. It might not be obvious at first. but it is a u sub problem. You would let this be your u, actually. And it should work out really well. Okay, what about number 3? This one's a substitution. What's the derivative of cot? So it's u sub because we have a cot and a cosec squared, and cosec squared is definitely related to the derivative of cot. The derivative of cot is just negative cosec squared. So that's a u sub problem, and so is the next one. Remember that when you do the derivative of a rad x, you get a rad x on the bottom. So that's also a u sub. In fact, most of these problems are u subs. As we go through them, you'll see that. This one, we have a 4t squared. Oops. We have a 4t squared, and we have a t. And you know that the derivative of 4t squared is linear. You know, it's 8t. So that one should be a u sub also. This next one, what do you guys think on this one? This one's more of a trig sub, because you could just write it as sec squared 3t, and then answers 1/3 tan t, 1/3 tan 3t. See? Because you're integrating sec squared, which is clearly a tangent. So that's almost a memorized one if you're willing to do one quick, identity. 1 over cos is sine, or 1 over cos is sec. So 1 over cos squared is sec squared. So that one's not nearly as scary as it looks. Okay, so I would call that, do we have an option called trig sub? Not really. Some people call it trig sub. You can just call it 3. Trig identities are helpful to us. What about the next one? Correct on that one. Somebody said that this one is a u sub also. We've circled the u, and the u is 1 plus sine, which makes a perfect situation for us because du is cos x dx. It's right there. Good job. So anytime we can find a function times its derivative, or a function divided by its derivative, or something like that, or excuse me, a derivative divided by a function, we can find that it's u sub ready. So like this one is u sub number 9. Number 9 doesn't really look like a u sub, but if you let this be your u, watch this. 1 plus cos squared x. The du is 0 plus 2 times cos x times sine x with a negative. So the du turns out to be negative 2 cos x dx, cos x sine x dx, excuse me. And I don't know if you remember this or not, but this right here, let me choose a different color pen. This right here is sine 2x. So we don't need like a ton of identities for the AP test, but it is helpful to know a few basics. So you can see that the numerator right there is really negative du. This is negative du up here. So this one is going to work out beautifully for us as a u sub if we use one trig identity along the way. All right, what about this next one? This is a tricky one. I see secants and tangents, so there might be a way to work things out. What's the derivative of tan? Sec squared, right? Do we see any sec squareds? Nah. Okay, well, never mind then. What's the derivative of secant? Sectan. Ooh, we might be able to make this work. I do see sectan in here. I do think there's a sectan in here. How about we rewrite this as sectan times another sec to the half. Now it's u sub ready. The u is secant x, and it is ready to go. The u is secant x. So I'm going to highlight your u and your du. This is actually your u right here. So you're going to have a square root of u. And your du is right here. So the yellow is your u, so there's a u to the half, and the du is perfect. Look at that. So I don't know, is that really a u sub? Yeah, it is, but there was a little bit of prep work to get it ready for u sub. That's normal. Not every u sub is like ready to, separate. So sometimes you have to kind of open it up a little bit and look at it fresh. So this derivative of tan x equals sec x, that didn't help us, right? What helped us is the derivative of secant. So, okay, let's erase this then. We didn't need this. Mr. Shore never actually used derivative of tan for that one. All right, so see, we're not going to finish them. We're just going to talk about each one. There are some toward the end that we will want to finish. Okay, let's go back up to the top and look at the next column. This one looks a lot like another one we already accomplished. Yeah, which problem number is it? Yeah, this is basically the same exact problem as number 6. So what do we do on 6 again? Let's go back. Oh yeah, we rewrote it first, and then we realized it was a memorized. So I'm sure you can figure out how number 11 is going to work. You're integrating cosec squared. How about number 12? Yeah, number 12. 2, memorized. Okay. Part of it is memorized. How about we break it up real quick? Just break it up one time so we can see it for what it really is. We've got an inverse tan, and there's also a 1 over 1 plus y squared. So one of these is the function, and one of these is the derivative. So who's the derivative? Arctan, or is it the 1 over 1 plus y squared? Okay, so this is the du. And then the other part is the u. So yellow means u. So it's really a u sub, but it again wasn't quite ready for u sub until we sort of wrote it side by side. Okay, next is, that one looks sort of like another one we did, but I think it's actually easier. It's a little bit easier than the one number, which one was it? A little bit easier than number 9. So I see a function, and if I take its derivative, I get another part of my integrand. This denominator. If you take the derivative of that denominator, you're going to get 0 plus 2 sine 2t. In other words, you're going to get 2 sine 2t dt. So the numerator is starting to match up. It's probably like negative half du or half du or something. It's very close to what du would be. So this is also a u sub problem. So I know it's kind of silly to just go through here and keep labeling which ones are u sub, but you can see that all u subs have one thing in common. The derivative is present, and so is the original function. The next one's pretty clear. This one was on the AP test you took, except it was a negative x squared. And it was an improper integral 1 to infinity or something? Yeah. Okay. On the 2012 test. The next one's a u sub. Here, this brings up an interesting question. On number 15, should we let our u be the cosine, or should we let our u be the sign, because the derivatives work both ways. The cosine's derivative is resembling a sine, and the sine's derivative resembles cosine. So which is the wiser choice for u? So we want to pick for our u, we want to pick the sine, actually, just the sine, not the e. And then the derivative will work itself out because it's cos theta d theta. So that's down here. Mr. Shore has a typo. This should say cos theta d theta, not cos theta dx. This is my one, or I have like two small typos on this worksheet. That should be a theta. There we go. But that is a u sub problem, technically. Okay, the next one's kind of confusing. We have square root of e raised to the x power, and then we have the square root of e to the x. But don't be fooled, they're the same thing. E to the rad x, I meant to say, I said that wrong. I meant to say square root of e to the x is e to the half to the x, which is e to the half x, which is e to the x to the half, which is e to the x inside a radical. In other words, e to the square root of e to the x is the same thing as square root of e to the x. So it's just, I was just trying to trick you. Okay? So they're exactly the same function. And they're both e to the half x. So think of this as e to the half x, sine of e to the half x. And then I think you can see that u sub is going to work out pretty good for us. Because the inside function could be a u, and what is the derivative of e to the half x? 1/2 e to the half x. So we're going to have an extra du outside there, so this should work out good. Okay, so we've already gone through over half of the problems, and we haven't solved them, but we've just been looking at them. Now let's go through and solve the rest of these, and that'll be our review session. Okay, so I'm going to switch just directly to pen, and you might want to grab a separate piece of paper for the rest of this because there's just no way you're going to fit it all on this piece of paper, you know. So we're going to solve e to the rad x over rad x first. Okay, so let me copy that over. So it was e to the rad x, and we're dividing by rad x. So e to the rad x divided by rad x. So you know, you can. The other thing about integration is you can always try something, and if it doesn't work, then just let it go. Just try something else. So I'll do the same color coding I did last time. This is a u, and this basically represents this represents 2 du. So our integral is e to the u times 2 du. All right, what's the antiderivative of e to the u? Yeah, e to the u. Right. So good job. E to the u. So it's 2 e to the u. And u here means rad x. And then how do we check our answer? That's actually really important, right? Why get a problem wrong if you know it's wrong? Why not just go back and redo it if you're positive, 100% sure it's wrong? How do we check to see if it's wrong? Or right, for that matter? Just take the derivative, right? We're finding an antiderivative, so might as well take the derivative. It's very easy to do, and you'll know you did it right or you'll know you did it wrong. Okay, so because it's 2 in front, you leave the 2 there, so we're checking. You take the derivative of e to the rad x, and you get e to the rad x times the derivative of rad x. And lo and behold, there's your integrand. How many of you are in the habit of checking after you integrate, you check real quick? Okay. The truth comes forward. Why not? I mean, it doesn't take long to take a derivative. You're experts at it. And you'll know if you missed a half or a 2 or something. Okay, let's go to the next one. So our next problem is at the top. Number 20, oh, no, it isn't. It's at the bottom here. It's e to the x plus e to the negative x over e to the x minus e to the negative x dx. So it's e to the x plus e to the negative x over e to the x minus e to the negative x dx. All right, so what do you guys think about this one? Do you see a function and its derivative? Not everybody sees it at first, but so which one should I call my u? So just make this my u? Well, then I'm going to have a u on top and bottom. One thing you want to do when you're finding your u is you want to find the most buried expressions you can. So the things that are sort of stuck inside a radical, or they're stuck down in a denominator, or they are stuck up inside of an e's power. The other thing, listen to this comment, this is really important. You want to make your e as complicated as possible without overdoing it. So it's a bit of trial and error, but it's probably not a good idea to just pick e to the x or just pick e to the negative x, but to pick a larger compound expression the same way Ashley suggested back here. Remember back on number 9? I think it was Ashley. She suggested we make the entire, actually I think it was on number 7. You said make the 1 plus sine x our u. Right? Yeah. You didn't say sine x, you said 1 plus sine x. That was very wise. It would not have worked out. It would not have worked out if we hadn't picked the more complicated binomial type expression. So I think you guys see it now, right? Yeah. What's our u? The whole bottom. It's true that the derivative of the top is the bottom, and the derivative of the bottom is the top. But we don't want u to be stuck on the top, because then du is going to get stuck on the bottom. See, we don't want that. So we'll make our u the bottom, the more buried expression. There's your u, and your du is the whole numerator. So it does take, it's kind of an art, you know, to learn this. It really is. You really kind of have to do a lot of problems, and you get pretty comfy with it. But okay, so this one's going to be pretty easy. I'm not even going to write let u equal. It's obvious. The bottom is the u. The entire numerator is du. All right, so now we just have du over u. Okay, I love this answer, though. It's kind of a crazy answer. We get ln absolute value u. Don't forget the plus c. Don't forget the absolute values. Okay, here's where it gets really kooky. The u was e to the x minus e to the negative x. Right? Okay, now, there are many ways this can be written. So I asked Wolfram Alpha to do this one for me, just for fun. And when I did it on Wolfram Alpha, it did not say this. Let me show you what it said. Wolfram Alpha spit this out at me. And I looked at that and I thought, where in the world did they get e to the 2x from? See? Well, here's the thing. Logs can be rewritten an infinite number of ways. For example, when I say that, what I'm saying is, like, let's say you have ln rad 2, right? That can be written as ln 2 to the half. It can be written as 1 half ln 2. It can be written as ln 2 over 2. It can be written as ln 8, and then put a 1/3 here. Like, there's so many ways you can rewrite a log. There's no end to it, actually. So because of that, we have to be real flexible with our answers, especially on multiple choice stuff on the AP exam. What if they offer the red? Are you going to recognize it's the same thing? Okay, Okay, so this is going to look a little crazy, but watch this. Here's how you convert, not the red answer into the blue, that's easy. But here's how you convert the blue answer to look like the red. They want an e to the 2x? Fine. I will multiply, if that's what they want, I will multiply the inside of this. I will multiply the inside of this by e to the x. Why? Because I need to. Okay, now you might say, that's illegal, Mr. Shore. Not if I divide at the same time. So I just put in an e to the x on top and bottom. That's perfectly legal, right? Top and bottom at the same time. Now I've got that e to the 2x when I distribute, right? E to the 2x minus 1, see it? And then there's another log that pops out. So I have this ln e to the 2x minus x, but then because there's an e to the x down here, I can subtract ln e to the x, and that's the x that they have here. So it's not obvious, but when I saw Alpha's answer, I was like, well, that's really weird. Why do they have an e to the 2x? And then I realized, well, if I multiply my inside and divide my inside by e to the x at the same time, I can make that happen too. You have to admit, their answer does look a little bit simpler. Like, the red answer does, I don't know, maybe a little easier to memorize, or, I don't know, maybe not. Okay, but that's kind of weird, huh? Logs can be written many ways. Let's go to the next one, ln x over x. We probably don't need to do this one. You guys have done many of these nested log ones, but we'll take a look at it. Pick a u. If it doesn't work, pick a different u. Okay, yeah, so you have ln x and you have 1 over x. And the derivative is the 1 over x. So let's pick our u to be the ln. We want to pick the u to be the ln. The du will be right here. So it's funny, we're doing antiderivative, but we're doing it by finding a derivative. It's kind of weird. It's a little bit crazy. Okay, so this is our u, and this is our du. Okay, so we end up with 1/2 u squared. And by u, we mean ln. So it's 1/2 ln x squared plus c. Kind of weird. Okay, let's go back to our notes here. We were also going to try ln rad x over x. Ln rad x over x. Okay, so somebody suggested that we write the x as x to the half. Right? I don't know, does that help?
Was that a good step?
It is a good step, actually, because there's another place I can put this half. Remember the rules of logs?
At the front?
At the front. In fact, we'll put it in the front, I like to call it. So in other words, this is the exact same problem we just did. What problem is this that we're doing now? This is number 20, but it is number 19 with a half in front. So what was our answer to number 19 again? Can't remember.
1/2 ln x squared plus c.
Yeah, so now it's going to be 1/2 times 1/2 ln x squared plus c. So it's basically 1/4. So the only difference is there's an extra factor of half that pops out. So while logs may annoy you sometimes, because of their many ways of being written, they may also bless you. So this is a blessing. The fact that we can move that half made this problem quite easy, actually. Okay, let's go to the next problem. Now we're getting into the 20s and 30s here, so they're going to get a little harder. And we will get a chance to see our IBP and so forth. Let's skip 21. Let's look at 22. So there's a danger of overthinking it. Do you remember when I had you put a number next to each problem to see what kind it was? What kind of problem is 22, actually? It is basic. Yeah, if you distribute this, it's just x minus rad x, which in turn is just x to the first minus x to the half. So it is just a basic algebraic, you're just going to be adding a power to each x and then dividing by the new power. So we're not even going to stress out about that one, we're not going to do it. So by distributing, you see it's just a polynomial style. Yeah, it's not technically called a polynomial, but it's you can use the power rule. Okay, let's go to the next one. (23). One minus ln is being squared. Boy, it'd be nice if that was our u. We're not afraid of u squared. Can we let our u just be 1 minus ln? So you guys see what I'm saying? Nobody really wants squared stuff. But if it's just u that's squared, who cares? Right? So let's pretend that that's u, see if it works for us. If not, we'll FOIL it out and do 3 integrals or something. Okay, so what is if our inside, if 1 minus ln t is our u, would that work for us? Can we just make that whole thing u? 1 minus ln t, make that our u. Du is, oh, what's our du? Negative 1 over t. Okay, we can move the negative to the other side. Did this work out for us? It did. It worked out beautifully to just make the inside, the entire inside, our u. And that's like what I was saying earlier about making your binomial expressions be your u. Let me ask you a quick what-if question here. Suppose that Mr. Shore had done this problem. I kind of wish I'd done it now. Suppose that this was not a 1, but a t. So we're still looking at 23, but I put a t minus ln t there. So in other words, the problem looks like this. Integral, oop, that's pretty, but that's weird. We don't need that. What if it was t minus ln t squared all over t? We can still do this problem, but can we make the u t minus ln t? What do you guys think? Can we let the inside be our u again? Yeah, this is going to be 1 minus 1 over t, and unfortunately we don't have a 1 minus 1 over t. We have a 1 over t. See the problem? Okay, so that's a real problem, actually. What it means is it's not a u sub problem. It just isn't that same kind. So what do we do in that situation? We can try integration by parts. We can try, tabular. We can try partial fraction. All those other methods are for these sorts of cases. But the other option is just FOIL out the top, so it looks like this. You know what I'm saying? FOIL it out into a trinomial, and then break it up into 3 separate integrals. 1, 2, 3. So you have integral of t squared over t. You have integral of negative 2t ln t over t. And you've got integral what? I don't want that thing. It's cool looking, but it's not what I want. Ln squared t over t. So the first 2 integrals are pretty easy, actually, right? But the third one is the only one that's going to give us a headache. And I think we can do that one by u sub. The third one is a u sub. If you let u be ln t, you see. So I guess the moral of the story is sometimes it's not a u sub, but then you kind of rewrite it, and then it is a u sub. That By the way, let's finish this one. I'm just curious how well you would do. So obviously the first one is just integral of t dt. So what's the antiderivative there? That's easy.
1/2 t squared.
Right. Okay. The next one is minus 2. Ooh, this is what I want to focus on. Do you have memorized the antiderivative of ln t?
It's t ln t minus t.
Good. Yes, it's t ln t minus t. Now, a lot, about, I would say, out of 100 students, probably 90 students don't know that. Because at some point you stop memorizing them, right? You're not going to memorize every single antiderivative out there, but ln is a pretty popular function. And if you should ever decide to study its area, it might be nice to know the ln antiderivative. So you're right about it. It's t ln t minus t. And the last one's a u sub problem, so we won't do it. But I wanted to hit that because, that is a pretty famous function, but like only 10% of people know it. You know what I'm saying? I'm making up that number, but I know for a fact a lot of my students don't know that particular antiderivative. What if you just can't remember something like what she just said, right? She just busted that out. Like, what if you didn't know that? What would you do on the test? IBP. IBP will give us the answer to that. Watch this. So let's say you're taking a test and you're like, oh my goodness, they want me to integrate ln. What am I going to do now? I can't remember. Is it x minus ln x? Forget. It's x ln x minus x, But how would you remember that? Suppose you don't. It's okay. That's what IBP is for. So we're supposed to pick a u and a dv. We don't have much choice for u. What do you have? I guess you're just going to have to pick ln x. You don't have a choice, right? So this is one of the beautiful things about IBP is even if you have no other choice and you pick this to be your u, you will learn something new. Okay, so watch this. What is the derivative of u? 1 over x. What is the antiderivative of dx? So this would just, if you integrate both sides like this, you just get v equals x. Okay, so not very interesting on that antiderivative. But watch this. Now we can do our oov minus, remember it's sfadu, which really means integral v du. Integral v du. And we get x ln x minus x. So the good thing is, if you do forget something, you might be able to recover it with your IBP. See how that worked out for us? Let's say you're taking an AP test and they ask you for this. Good luck, right? Does anybody, we know the derivative of arcsine. Maybe review it, right? We'll review it. We plan on reviewing the derivative of arcsine, but what's the antiderivative? Nobody knows. I don't know either. I can't remember. But watch. If forced to do something like this, we might be able to get away with IBP. Let's say u is arcsine, because we don't have a better choice, and dx is our dv. We can do this. What's the derivative of arcsine? Rad 1 minus x squared dx. And then v would just be x. So oov would be x arcsine x minus sfadu would be this. And this can be solved by u sub. Just let u equal 1 minus x squared. So you could get it. You could get the antiderivative of arcsine by using IVP. It's a great method. Okay, let's go now to, where were we? 24. 24 is the hardest problem on here, bar none. Like, there's not even a comparison. Okay? You're not going to believe your eyes when you see how this one is done. And I don't need you to know it, but I'd like you to appreciate the solution for what it is. Don't even bother writing it down, just enjoy this. I needed a little bit of help here from Wolfram Alpha to figure this out. A lot of help, actually. Okay, so watch closely. We have something that doesn't look like a U sub. It's not an algebraic. It's nothing we've seen before. Might try some kind of a substitution and then go arc trig or something. I don't know. So here's what they suggested on Wolfram Alpha. And I have not decided if there's a faster way yet. Sometimes we just put something that's on top at the bottom of the bottom. We've done this before. We do it with L'Hopital's rule sometimes. Also, sometimes we take things that are both in a radical and put them under one roof. Right? Okay, now if I let u equal 1 minus x over x, du would be low d high minus high d low over low squared. In other words, it's negative 1 over x squared dx. So a quick substitution, let's see here. We would want to replace this part with u, and dx, let's see, dx, what can I replace that with? Oh, here we go. I'll take this statement and I'll isolate dx. So negative x squared du is a good replacement for dx. So it's going to look like this. Integral 1 over rad u times negative x squared du, and x squared, if you go back up, see where it says u is equal to 1 minus x over x? I can cross multiply that and get xu equals 1 minus x. I can bring all the x's to one side and factor out an x, and I can write that x is 1 over u plus 1. Therefore, x squared would be 1 over u plus 1 squared. So this integral can be written as 1 over rad u, there's a negative, and this is just 1 over u plus 1 squared. And most people would agree that it looks like I've made a bigger mess of things. Okay, now I'm going to let t equal rad u. That means that dt is going to be 1 over 2 rad u du. In other words, it's going to be, if I rewrite this, it's going to be 1 over t, and then it's going to be, let's see here. Oh, t squared would be the same as u. So this would be a t squared plus 1 squared. And du would be 2 rad u dt, or you could just say 2t dt. So this is a 2t dt. And then this t cancels out. So now we have negative, then we have a 2 over t squared plus 1 squared dt. So it's like, wow, I've got it all down to a single variable. Look at that. Like there's not two parts anymore. Now I don't know what to do with t squared plus 1. I don't know what to replace that with. But what if t was a tan theta? I'm going to let t represent tan theta. Because I don't know what to do with t squared plus 1, but I've seen tan squared plus 1 before. I'm going to just let my t represent tan theta. And that means if I do that, then dt is going to be sec squared theta d theta. Okay, so now I've got it down to this trigonometric looking thing. And tan squared plus 1 is sec squared. So this is sec to the fourth. This is so cool. This cancels out, leaving you with 2 secant squareds on the bottom, or 2 secants on the bottom, I mean. Sec squared on the bottom is the same as what on top? Cosine. Can you believe it? We did it. Okay, how are we going to integrate cos squared? You can use IVP. You can use trig identities. It's the same as 1/2 plus 1/2 cos 2 theta. And then we get 1/2. I'm going to pull out the half where the negative is. And then I'm going to have basically integral of 1 plus cos 2 theta.
Did you forget a 2?
I might have forgotten a 2. Where is it?
If you scroll back down a little bit. It's like 2 over secant squared.
Was there a 2 out front? Let me check my work too.
There's a 2 on the top.
Yes, there was a 2, and it's from a couple steps ago. I just miscopied it. There was a 2 right here, and I forgot to put it there. Thank you. Almost done, guys. Hang in there. So that 2 is right here. Okay. All right, so now we have basically, let's see, I got to integrate this. Theta plus 1/2 sine 2 theta. Okay, here's where it gets tricky. I've got to change it all back to x. So what was theta again? I think t was tan theta, right? So this would be arctan t. So theta is arctan t. So this is a negative arctan t. And then I have a 1/2 sine 2 theta. So that's 1/2 times, think of this as 2 sine theta cos theta right here. This is the same thing as 2 sine theta cos theta, so these cancel out. Okay, so then I need to draw a triangle where this is theta. Oh no, this is the, this is the angle theta, and then the opposite side is t, and the adjacent side is 1. So tan theta is t. I told you this is a crazy problem. Okay, so what is sine theta? It's t over square root of t squared plus 1. And what is cos theta? It's 1 over square root of t squared plus 1. Don't forget the plus c, right? Doesn't seem very important right now. That's how you get it back to t. But hold on, t was the same as, where did we get the t from? Let's see. T was tan theta. Oh yeah, t was rad u. T was rad u. Remember that? I remember that. T was rad u. So this is a rad u. This is square root of u plus 1. This is the square root of u plus 1. And I think at the very beginning we said that u was, this goes way back, u was 1 minus x over x. 1 minus x all over x. So here's the answer. Ready? Inverse tan, the square root of 1 minus x over x plus, and then this is just a rad u on top, so this is square root of 1 minus x over x. And there's a u plus 1 on the bottom, that's 1 minus x over x plus 1 plus c. Done. Okay, why in the heck would I do this for you? I want you to see that after many substitutions, we did integrate it. And then we had to go back and fix everything, but you can see a u sub is actually a very powerful method. We did a u sub, t sub, a theta sub, and trig. Trig helped us out. We got stuck when we didn't know how to integrate t squared plus 1, but we happened to know what tan squared plus 1 is. So we pretended that t was tan theta. And we made it work. Okay, that's obviously overkill, but That's how you do it, or one way you could do it. Anything shorter than that is just pure elegance, like genius kind of stuff. People who see it and they're like, oh, I see it. That's easy. But those kind of people, we just say, okay, you be you and I'll be me. Okay. The last few on here aren't nearly that hard, but they all have something interesting to say about them. This problem can be solved by letting u equal 1 plus x. Okay, I'm going to pause my video and let you try it real quick. Okay, so we know that du is just dx. Did you guys get that far? Okay, so here's the trick. You can rewrite this part as rad u du, but what are you going to do with this little x out here? You can't leave that there. You know what I'm saying? Can you think of a way to write x so that it looks like u's? U minus 1. Yes. Obviously, we would want to put parentheses on it, right? So it's going to be a u minus 1 right here. Now, it seems like we're kind of reaching a dead end, but isn't that the same as u minus 1 times u to the half? And then can't we just multiply these together, like distribute? So we get u to the 3 halves minus u to the 1 half du. So we end up with 2/5 u to the 5 halves minus 2/3 u to the 3 halves. So we ended up just adding a power dividing by the new power. Interesting ending. Now we can go back and change the u to x plus 1. This method is a little bit different from u sub. Do you guys agree? It's got a little bit different feel to it. It wasn't just finding a u and a du. It was also replacing other x's with u's. This is called change of variables. Change of variables. You're actually literally rewriting the problem. It's really a u sub, but it's got a slightly different feel to it, doesn't it? So you guys see what I was saying earlier about Madeline's work? We kind of have to do it Madeline's way sometimes. Rewriting that x as u minus 1. Yeah, good eye on that, Haley. Okay, let us now go to the next problem. 2x over 4 minus x squared. 2x over 4 minus x squared. This is a u sub problem. You guys agree? You can just let u equal 4 minus x squared. And in fact, besides the negative, really your whole numerator is du. So that top is just negative du. And the bottom is just u. So we end up with negative ln absolute value u. And then we can plug in our 4 minus x squared. Okay, so this one's pretty straightforward. You guys told me you were going to start checking your answers, right? Take the derivative to make sure it comes out to 2x over 4x minus x squared. Okay, but look at the next problem. It looks very much like 26. Very much like 26. What's the only difference? Look at the numerator of 27. What's the only difference? It's missing an x. All of a sudden, lo and behold, this is not a u sub problem. See what I'm saying? So what kind of problem is it? This is a partial fractions problem now. Okay? So you're going to split this up into something over 2 plus x plus something over 2 minus x, like that. You need to figure out the a and the b. Let me rewrite that. So you want to think of the fraction 2 over 4 minus x squared as the same thing as this, right? So when you put these together, you can multiply this to here and this to here and these together. So it's going to look like this. It's a little hard to follow those arrows, sorry. This gets multiplied to there. So follow the green arrow, follow the purple arrow, follow the red arrow. So it's going to look like this. 2 minus x times a plus 2 plus x times b. When the bottoms get multiplied, it goes back to 4 minus x squared. So since the bottoms are already the same, we don't really need to look at those. But we do need the tops to be the same. So you're going to write 2 equals 2a minus xa, and then plus 2b plus xb. If you organize this by x's versus non-x's, you have b minus a for your x's, and you have 2a plus 2b for your non-x's. Now look at the left side. What do you notice? There are no x's, so you could put a 0x there. So this tells us basically that b minus a is 0, right? And 2a plus 2b is 2. There is a faster way to do it, but it's a trick, and I don't teach tricks. Because tricks don't retain. You don't remember them. You don't know why they work. But you know why this works. You're trying to make them equal. So I'd rather not teach tricks. You really need a trick the day before the test, I'll teach it to you. And you'll remember it one day later, but you won't remember it in two months. Right? Or you won't understand it at least. This way you don't have to understand. Just organize it. Okay, so this means that a minus b is, or sorry, b minus a is 0, and at the same time 2a plus 2b is 2. So the first statement is saying that a is the same as b, and if that's the case, then we can put 2a plus 2a equals 2. You know, you can change the b to an a. So you end up with 4a equals 2, which means a is a half. You guys are probably wondering how I'm writing in such beautiful calligraphy. I chose a calligraphy pen. This means b is also a half. I'm like, man, he writes fast calligraphy. Okay, so a and b are both a half. Now go back and do the problem. Like integrate it. Now that you know a and b are both a half. So since you were integrating a over x plus 2 plus b over x minus 2, or I meant to say 2 minus x. It was 2 plus x and 2 minus x, right? So I can write the x, the 2 plus x as x plus 2, but I cannot write the 2 minus x as x minus 2, right? But here, watch. I don't want to have any weird chain rule stuff, so I'm going to go ahead and put an x minus 2 here. I just have to put a negative in the middle. Okay, so I purposely put a minus in the middle here, and I made this bottom an x minus 2. That was on purpose. This is going to make my integration a little bit easier. So now I'm just going to pull out the halfer. And this is just 1/2, and there's 2 logs. There's ln absolute value x plus 2 minus ln absolute value x minus 2 plus c. Okay, so you can put those together if you want to. So you can write your answer like this. That's one way to write it. Or you can leave the half out front and collapse everything into one log. I do think the absolute values are important though, so keep them there, regardless of which way you do it. Or you could bring that halfer up and just make like this a big square root. So there's lots of neat ways to write logs, as you know. Infinite number of ways. I've seen their answers written all 3 of these ways. Well, actually, the first 2 ways on the AP test. I've seen him do it both ways, first way and second way. I don't think I've ever seen him do it the third way. Are we on the last problem yet? I think we're on the last one. Oh, we don't have to do this one entirely. This one is also partial fractions. But let me tell you what I got for my A and my B. Look at 28. For my A and B, I got, I'll tell you right now. You can do it at home. Part of this is for you to practice at home. When I did my A and my B, for A I got -5/4, and for B I got 3/4. So that's a very different feel, isn't it? Different numbers there. Okay. They're not like both half or whatever. I do want to mention the last two problems. Sorry I'm keeping you late. Does anyone need to leave? Okay. Okay, for 29, we have sine x over 1 minus cos squared. Is the calligraphy pen okay? It's cool looking, isn't it? So you could try like a use sub sort of thing, but it's probably not going to work. The best thing to do is just, oh, did I copy this problem wrong? I did, didn't I? The top was what? Oh, the top was sine. Oh, and the bottom was also sine. Yeah, you're right. I remember now. Okay, so the top is a sine x. The bottom is just 1 minus sine squared is the same as cos squared. Okay, so now you can rewrite this. You can actually do a u sub if you want, but I'm just going to write it like this. Think of it as sine times 1. So let's see, we have a sine over cosine. That's a tan. I think I said it wrong to a student that just left. It's not a cotan, it's a tan. And there's a secant. There we go. And this is exactly the antiderivative, or the exact derivative of sec. So you're done. So that's kind of a fun one. It's not even complicated, but you could definitely get off on the wrong foot. You know, if you started with some kind of a crazy partial fractions thought or whatever, that wouldn't work. So last one. This is a long session. Thanks for staying. Our last problem, let's go and write it out. It's 4x minus 1 over x squared plus 9. And we're going to split this into two parts. Notice you cannot use partial fractions because x squared plus 9 does not factor. At least it doesn't factor into real stuff. You might be able to use complex, like i's and stuff, and do some kind of weird partial fractions thingy, but I haven't really thought about it. Okay, so let's break it into two problems. Nothing wrong with that. And we're definitely going to treat these separately. The first one's a u sub, so you're just going to let u equal x squared plus 9. Du is 2x dx. In other words, 1/2 du is x dx. Okay. So we have basically integral of 4 times 1/2 du all over u. In other words, 2 integral du over u, or 2 ln absolute value u. So we got 2 ln absolute value of x squared plus 9. Okay, the first integral's done. Good riddance. Unfortunately, that was our easier of the two integrals. Shrink that a little bit. So we can go up and see the other integral that we had. Okay, what is this thing? Well, it looks kind of like, it resembles this rule. Remember that the derivative or the antiderivative of 1 over 1 plus x squared is arctan. You might remember that one. This has that feel. It definitely has that feel. So that's we're going to manipulate this and make this work for us. Okay, first we can't have a 9 plus x squared. That is not going to work. We're going to have to make that a 9 into a 1. So how are we going to make the 9 into a 1? Divided by 9. It's your only option. Don't say subtract 8. That won't work. So we're going to divide this by 9, which means we have to divide this by 9 and this by 9 all at the same time. We don't have a choice. Okay, so now it looks like this. We have a 1/9 dx, and on the bottom we have basically an x squared over 9 plus 1. So we're able, if we put the 1/9 in the front, we were actually able to write this as 1 plus something squared on the bottom. That's good. But it isn't an x. It's not an x squared. It's an x squared over 9. That's okay. We're going to change the x squared over 9. We're going to write it as x over 3 squared. See? We need it to look like something squared. So it's x over 3 that's being squared. You might remember doing this from homework way back in chapter 3. Okay, now we'll do a quick little u sub. We will let u equal x over 3 so that du is 1/3 dx. In other words, 3 du is dx. And we can rewrite this as 1/9 integral 1 over u squared plus 1 times 3 du, and I'll go ahead and put the 3 out front. Getting there. So this is 1/3 arctan u, where u represents x over 3. Okay, here's our final answer. Our first integral gave us 2 ln x squared plus 9. Our second integral gave us 1/3 arctan x over 3. There's your answer. So sometimes you'll be poking around on Wolfram Alpha and you'll see a funny answer like this and like, an ln and an arctan? That's because the original problem got split. You guys understand what I'm saying? Remember the first thing I did on this problem? It was the very, very first step. It was the very first thing I did. I broke it up, yes. And that's why we got 2 different types of answers. So that's an option for you. If you have a problem, you can try splitting it into 2 parts. So there's plenty of practice for you on there, because I purposely left many of them unfinished. But some of the weird ones we went ahead and followed through with.